Wasabi, you guys. Welcome to the second lecture of linear algebra. Holy hell! I'm getting used to this. But it's a very fun teaching experience. Okay, so in this second lecture, we'll be doing matrix algebra. Alrighty, the fun stuff begins with matrix algebra. Now, let's recall some stuff, right? Now, yes, this is an ugly matrix. It's nasty, some random pi right there. But we're not going to do anything. Trust me. If there's no augmented matrix, that's it's just to show. It's just an example. So, with this matrix, what do we, if I tell you what is the size of a matrix, what is the size of a matrix? It's, again, to recap, we go by row by column. So the size of this matrix A is a 4 by 5 matrix. Okay, so we have a 4 by 5 matrix. And then let's say if I asked you, all right, what are the entries? What are the entries? What are the entries? What is entry A12 and A34, right? If you see this notation here, right? If you see this notation, this means that these are entries. So the way we read it is, okay, so what is the entry at row 1, column 2? Row 1, column 2. So it seems that A12, this entry is 2. Okay, what about entry 34? Row 3, column 4, this is 6. So entry 34 is 6. Okay? There are also other notations that I'm just going to help you get used to. These are new. These are new notations that I'm going to show you. Right. So if I say second row, what is the second row of A? Right. Second row, I'm just making you get used to these letter notations. Second row of A is, in the way we notate this is A2. A2 is equal to -2 here, right? Our second row is -2, 0, 20, a random pi, -4. Okay. This oh god. Don't lag. Okay. Oh god. I'm slowly lagging. That's okay. So this is our second row of A2. Okay? Now, what if I told you what is the third column of A, right? Then the way we write this, the third column of A, and the way it's written is capital A3. A3, the third column is 2, 20, 3, and 5. Okay? So the third column of A is A3, this. Okay, this is our third column of A. Okay? So that's it. I just want to make you be aware of these notations. That's it. It's just to kind of show you some notations, as well as to recap what these are as well. Just entries. Okay? Alright, let's get to the fun stuff. So now let's get into some matrix algebra here. So, let's start with matrix addition. The easiest, well, in my opinion, this is the easiest. But in matrix addition, if you don't remember how to do matrix addition from pre-calculus, or you never learned it in pre-calculus, that's okay. It's actually very straightforward. Let me actually use yellow. So the way we add matrices, so first off, the sizes of the matrix has to be the same, right? If they're different, if both matrices are different sizes, then you cannot add them. It's not defined. Okay. So 2 matrices must be the exact same size, and in this case, they're both 3 by 3 matrix. So we go ahead and add these two, right? And the way you add it is you pretty much just add by entries, right? So 1 plus 1 is 2. 0 plus -1 is -1. 1 plus 0 is 1. 2 plus -1 is 1. 3 plus 0 is 3. 1 plus 1 is 2. And then you just keep going. You just keep going and going. And you have your answer here. I drew it very crooked because I am literally sideways because of my room. That should look nicer. There you go. Okay. Okay. So this is our answer. That's it. It's very straightforward. So matrix addition, right? You just add up the corresponding entries. Okay. So now what about scalar multiplication? It's also very straightforward, right? So sometimes we could actually use a number, right? We can use a number to just multiply everything. That's what this means, right? So you're doubling the matrix. That's what that is, right? 2 times something means something added twice, right? I guess a great way to put it is like, I don't know why I was gonna put it in front of me, but here, right? 2m is equal to m plus m, right? That's what that is. That is why 2 times a matrix, you're adding this matrix twice, which is why it is allowed that we could just multiply 2 to every single entry. So the answer to this is 2 times this. This is 2. 2 times whatever, all the zeros is still 0, right? 0. We have 2 times 1 is 2. 2 times -1 is -2. 2 times 2 is 4. 2 times -1 is -2. And then 0. Okay? Because like I said, it's literally just adding matrices twice. Okay? And that is scalar multiplication. And now we also have some special matrices that you must know and that you will come across in linear algebra. So this is called a zero matrix. And to demonstrate what this is a 0 matrix. It could be any size, right? It could be any size. It could be a 3 by 3 full of zeros. Literally any matrix, any size filled with zeros. In fact, if we want to be specific, they would write it like this, where it represents m rows, n columns. So OMN is just to generalize it, I guess. It looked like this, kind of like the intimidating diagram that we did in the past lecture. So literally any size, whatever. But don't look at this because this looks very intimidating. Again, just O is just any matrix filled with zeros, for any size. Okay, so this is called a 0 matrix. And so when you see an O, that's what that is. It is a 0 matrix. Okay, another identity, or, well, I just said the name. Very good recall. What is a pivot column? Pivot column is a column with a leading one, right? This here, right? This identity matrix is filled with pivot columns, right? That's what it is. A pivot column, and a pivot column here, right? It's a leading one with nothing above it. no non-zeros entries above it. Okay, so this is an identity matrix. Okay, this is a 3x3 identity matrix actually. If we want to specify, right? So in this case, we would call this I3 if you want to specify, but I mean, dealing with whatever problem it gives, we can just leave it as I. But to be specific, right, we would write it like this. I3, right? If it says I2, then it's a 2x2 matrix, and you would write it like this. Okay, that's an identity matrix. All right, and then of course, if you want to generalize it using that intimidating picture again, for however many n by n matrix. Okay, so again, just to remind you, I must be a square matrix. Okay, it must be. Must be a square matrix. Okay, it is a square matrix filled with pivot columns. Okay, it is a square matrix filled with pivot columns. So this is called an identity matrix. Okay, zero matrix, identity matrix. You're going to see that a lot throughout the linear algebra course. So now let's get to the most annoying part. Well, not most annoying. Only if you do it with bigger matrices. But yes, we have matrix multiplication. So first off, I just want to reiterate: let A and B be matrices, right? If we multiply A and B, it is only defined, meaning that it has an answer, if the size has to be like this: an m by n and an n by p. Okay, and let me tell you why. The reason is we have to remember that in matrices, well, actually, no, I did not show you. So because of this, right, in algebra, multiplication, this is true, right? Well, in matrices, this is not always true. Okay, this is not always true. It is not always true, right? Just because A times B does not always equal B times A, right? In this case, with that matrix right there, that yellow matrices, it will not satisfy this. Okay. Now, again, it must have a size m by n, and a b must be n by p, where we have n's. The n's has to be the same thing. Okay. What if both matrices are square matrices? That's perfect. It's easy to see that they can easily be multiplied. Square matrices can perfectly multiply to each other, right? But whenever you get something like rectangles, it must be like this: n by n and n by p, just like this, right? So here we have a 3x2. Okay. So we have this, a 3x2, and here in this matrix we have a 2x3. Okay. Can we multiply them? Yes, we can. Yes, we can. Because these two are the same thing. They're the same numbers, right? We have 2 and 2, right? It's like n and n. M by n, n by p, right? Because they have the same number right here in between, then you can multiply them. In fact, this will come out as what we have left over. This will come out as a 3x3 matrix. I know, very wacky. Okay, in matrix algebra, it can be a little wacky, but you'll get used to it. You'll get used to it. Okay, so this comes out to be a 3x3 matrix. All right, now that we know that this would come out as a 3x3 matrix, let me actually switch it around. I can actually switch it around. Let me show you why I'm going to switch it around. Okay, again, this is not true. is not true for all matrices. Okay. Are we allowed to do this? We have a 2 by 3. And we have a 3 by 2. Can we use multiplication? Yes, we can. Yes, we can. Right? These numbers are the same. So that means that with these two outer ones, we will get, this would come out as a 2 by 2 matrix. Oh, thank God. Okay. So now this will come out as a 2 by 2 matrix. Okay. So here's how we do it. Okay. Watch very carefully. All right. My fingers, hopefully you can see my finger here. Okay. So here, 1 times 1 is 1, plus 0 times 3, that's 0, plus 2 times -1, it's -2. So 1 plus 0 plus -2, that's -1. Okay? And you continuously do that for every row and column. So let me, if I erase this, right? So we go here and go like that, right? That's gonna fit this here. Okay? So what we're doing is, okay, so we do from 1 to 1, it's 1 times 1, plus 3 times 0, plus -1 times 2, right? That's what that is. This is equal to -1, and that's where we put this at. We put it right there, okay? And then we do the same exact process, right? Here, but now, instead of here, it's here now, okay? That goes here, okay? And in this case, we have 1 times 0 plus 3 times -1, and then -1 times 1, that's -1. This is what, -4? So we have -4 right here. Okay. Next, we go at the bottom now. So now this is where the bottom goes. So here, all right, to the left side. Because it's this left side, we go bottom left side. That's how matrix multiplication works. But you'll get the hang of it. You'll get the hang of it. All right, here, -1 times 1, okay. 0 times 0, that's 0. 1 times 2, that's 2. So we get 1 here. So 1 goes in here. Okay. All right, let's continue. All right, last entry. We have this bottom, and then to the right of the bottom. That's a very bad circle, but to the right. That's, wow, that's surprisingly ugly. For your perspective, like that. Okay, so that means we have -1 times 0, that's 0. 0 times -1, that's 0. Plus 1 times 1, that gives me 1. And that's what we put here. Okay? And that's how you do matrix multiplication. I know it's a little confusing, but that's the process of matrix multiplication. So it's, again, unfortunately, here in VR, it's weird to see my arms. Let me see if I go like this. Right. If I can stop lagging, perfect. So pretty much what we do is we go this way. So this is top left, top right, bottom left, bottom right. Okay, and if it was bigger, right? If it was a bigger matrices, then it's like, this is for the first row, first column, first row, second column, second row, first column, second row, second column, right? So whatever you're multiplying it by, depending on what row you're using and what column you're going by, that's where the answer goes to that specific entry, right? So if I'm going here, adding by this, 1 times 1 plus 0 times 3 plus -1 times 2, right? We add those two together, and we put that answer where it is at first row, first column. So we put that answer at first row, first column, in which what we do. Okay? Alright, we'll get used to it. We'll get used to it. It's a lot of practice. You just practice a lot, and then you get the hang of it. And it turns out it's not so bad. I will not give you like very big matrices. Like that's a little unnecessary. Other than that, you could just use a calculator. That can work. Okay, but that's how you do matrix multiplication. All right. Now that we know how to do matrix addition, scalar multiplication, matrix multiplication, and then we also know identity matrix and a zero matrix, we can now start getting into some matrix algebra properties. Okay, so I won't be listing the obvious or the clear obvious ones, just like some questionable properties. So, of course, if we have 3 matrices and we have something like this, multiplication like this is also the same thing as A, and then multiplying BC first and then times A. They're going to equal. Okay. So in algebra, they call it associative property. So pretty much they equal. If you multiply AB first, then times C, it'll come out the same result as multiplying BC and then times A. Okay? Second property is we have A times B plus C. Okay? So whenever you have this, right? In matrix algebra, it works the same way as distributive property. So in distributive property, this also works. AB plus AC. Okay? It works for matrices as well. Okay. Third property is for the identity matrix. If you remember the identity matrix, AI is equal to IA is equal to A. So pretty much the identity matrix, it behaves like the number 1 in multiplication, right? If you multiply any number with 1, it just becomes itself. That's literally how identity matrix works. If you multiply an identity matrix to any matrix, it's just going to equal A. It'll come out the same thing. Okay? And of course, if we use a zero matrix, right? If we use a zero matrix, you're just multiplying everything by 0, right? All the entries are just being multiplied by 0. It's just going to turn out as 0. Okay? And that's it. I think this is like basic matrix algebra properties, but I just want to let you know in case if you're wondering, this also works in matrix algebra. We can also have exponents as well, right? So if we have a matrix A, okay, if we have a matrix A, and we use the exponent 0, right? It's kind of like, like algebra, 2 to the power of 0 or any number to the power of 0, it's just going to equal to 1. So it's exactly like this, but instead of 1, it's a matrix. So a to the power of 0 is equal to I. Okay, not a 0 matrix. This is it's a 0. It's a 0. Okay, a to the power, the matrix to the power of 0 is equal to I. Okay, now how about a square? Right, a square, it's the exact same thing as just multiplying a twice. Right, that's all it is. You're doing matrix multiplication with the same matrices. And in fact, you can do the same thing with a cubed, right? Multiply matrix A 3 times. That's what that means. And then you can do however many times you want. A to the power of k, where you could be multiplying it k times. A times whatever, k times. That's what that means. Okay? Can you have a negative exponent? Yes, but we won't go through that yet. Can we have a square root or a fraction exponent? We will not go over through that because that's a very advanced math topic. Okay. We will not be using fractional exponents in matrices. Dear God, no. All right. Let's go to the next content. The next topic is a transpose of a matrix. So we have a transpose . Oh my god, I can already hear the puns. Transpose of a matrix. So pretty much what I'm saying is the entries of the rows, will swap places with entries of the columns. So pretty much every entry, mn, swaps places with entries in the position of nm. Okay, that's what a transpose of a matrix means. So let me go ahead and quickly demonstrate that. We have a matrix like this. Okay, so what that means is we'll be swapping this. So then this will be our column. Each row will become our column, and each column will become our row. So what that would look like is that the transpose of A. So because this is a 3x4 matrix, it's going to become a 4x3 matrix. So now we have 1, 0, 0, 1, 1, 0, 0, 1. Okay? And then we're going to have 2, 1, negative 1, 2. Okay? Then next is we have 0, 0, 0, 1, 3. Okay? And there you go. That's the transpose of A. Okay? Now, I do want to mention. Ooh. So, I just want you to be very careful. So it looks like we rotated it like this. Oh, well, in your perspective, we rotated it like this. But it's not rotating it. Okay? I want you to just keep in mind that we are not rotating a matrix like this. We are not, I'm going to repeat myself, we are not rotating a matrix like this. Okay? It's not the fact that we rotated it. Okay? Red means wrong. Okay? We did not rotate this. Okay? We did not rotate this. What we're doing is we are swapping We are swapping rows and columns. That's what we're doing, right? We're swapping rows and columns. We're swapping entries. We're swapping entries. Yeah. In this case, that's what we're doing. Okay. In a square matrix, it's very easy to see what transpose of a matrix looks like. It's easier to see it in a square matrices, but in a rectangle, it looks confusing because it's not really symmetrical. But I'm gonna delete this blue arrow before I confuse you. But yeah, all what's going on is, entry 1 2 becomes entry 2 1, which is exactly what happened here. Entry let's say this is 3 4 becomes entry 4 3, which is exactly what happened here. Okay, so we're pretty much swapping entries mn to entries nm. Okay, and that's how a transpose of a matrix works. And the reason why we have this function is because sometimes when you work in 3D modeling, I guess for programming, for Comp-Sci, when you work with 3D models or 3D structures, transposing it there's like a specific transformation that it does. I don't know exactly. I could be wrong. But it's to help edit a specific 3D object. But that's just my awareness. I could be wrong. Don't take my word for it. But you do use it in some programming applications. Okay. And now that we know what a transpose of a matrix is, here are some properties. Yes, we got transpose properties. Transpose properties. Okay. If you want to transpose a transposed matrix, you're just gonna get A back. That's it. So if you're just curious, like what happens if I do it twice? You just get the original matrix. Okay. Property number 2. If you have a scalar or some number that you multiply with, right? I don't think I defined a scalar. A scalar is pretty much, it's just a constant. A scalar is just a constant, right? This is a scalar. It's just like a constant. When I say constant, I mean like just like any number, like 2 times a matrix. We call it a scalar in linear algebra. Okay, so here, I'm sorry, I did not write that correctly. If we are transposing, if my stick drift can work with me, transposing a number times a matrix, this would just come out as a number times multiplying a transposed matrix. Okay. Number 3 is whenever we're adding, when we transpose a addition of matrix, this becomes an addition of the transposed matrices. Okay. I'm gonna rephrase this because we are working with matrix addition. A and D are same size. Okay, I almost lagged. But yeah, A and D must be same size. Okay. And now number 4, right? What if we transpose a multiplication of matrices? Then what you would get is a transpose of B times the transpose of A. Okay? Again, where AB exists or defined, right? As long as you can multiply those two matrices, then that's what it would look like when you transpose of a multiplied matrix. Okay, and that's it. Those are the 4 transpose properties. Now, relating with transpose of a matrix, we have another special type of matrix. Now, you're probably thinking, what on earth does that look like? Well, here's what it looks like in a square matrices, right? If we apply, here are some actually, I'll demonstrate a regular matrix, right? I'm going to start with a 2 by 2 because it's easier for you to see, right? So if this is A, then the transpose of A, let's see, swap, it's going to be the same thing, right? So AB becomes our column, AB, okay, right? AB is a row here, it becomes our column, and then CD here becomes our column right here, CD, right? And notice that AC, this column, becomes a row, okay? So that's what a transpose of a matrix would look like. Notice that in the square matrix, the only thing that switched is this. So that's what I mean by, like, in square matrices, it's easy to see what the transpose look like, because in a square matrix, the only thing that switches is just the diagonals. That's all it is. You just switch the diagonals. And you do that, including for like bigger matrices, right? If I had something like, I don't know, X, B, Y, or some big matrices, right? If I have a big matrix, right? If I want to transpose this big matrix, these two would swap, and these two would swap. It's like a reflection here, okay? It's like a diagonal reflection. We're swapping diagonally. That's why when I say when transposing a matrix, it's not a rotation. It's like a reflection in a way. Okay. So now with that, what does a symmetric matrix look like? Here are some examples. Right. A good example is the identity matrix. The identity matrix is symmetric. Why? Because it is reflective in the diagonal, right? If I were to like go like that, right? I am literally swapping this, swapping this, swapping this. It does not change, right? It's symmetrical diagonally. Okay? Now, any other examples? Of course, there are much more examples, right? I can go ahead and draw or write down a random matrix here, right? 1, 2, 5 here, okay? Just, it could be, the diagonal can be literally any number, and then if I put a 3 here, then I have to put a 3 here. If I put a 4 here, then I have to put a 4 here. You see how I'm reflecting by the diagonal? If I put a 1 here, I have to put a 1 here as well. Okay? That's what that is, right? If I were to transpose this matrix, this swaps places diagonally. And it's easy to see that in a square matrix, right? In a rectangle, not so much, because it's not a perfect diagonal. So you would have to actually go by swapping rows, swapping columns. Okay, but in this case, we can easily see that this is symmetrical. Okay, it's a symmetric square matrices. Symmetrical square matrix. And now if we put it in letters, like generalizing it, right? We have A, we have B, C. Then we also have to put B, C here. D. If I put E here, I have to put E here as well. Then F. This is our generalized symmetric matrix. Okay? And that's what a symmetric matrix looks like. So this is called a symmetric matrix. A square matrix, is symmetric when A is equal to the transpose of itself. Okay? I forgot to mention that for symmetric matrices, so pretty much what's going on is entries, entry mn is equal to entry nm. So this is another way of thinking of it, right? A symmetric matrix, in order for this to happen, right, for a transpose of matrix to equal to its matrix itself, the entries have to equal, right? The transpose entries, right? The reflective, right? The entry of mn must equal to the entry of nm. Okay? That's one way of defining a symmetric matrix. Every entry of a symmetric matrix must satisfy this. Okay? And that's why the complete diagonals will always be unbothered, because, you know, A11 is equal to A11. You know, they're the exact same thing. Same goes here, A22, A22, right? Exact same thing. That's literally, you know, the diagonals, whatever stuff is, diagonals. A33 is equal to A33 if you swap it, right? And then the rest here will have to be swapped, you know, when transposing. So that's another way to look at symmetric matrices. Okay? All right. Next thing is vectors. Now we're going to get into some vector stuff. So, what is a vector? You probably heard me. If you remember what I mentioned, a vector, well, it's most commonly a column matrix. So, in linear algebra, we mostly use V. Sometimes it's like bolded, a bolded V, and we write it like this. Okay. So I'm just going to write as an example. I'm not going to generalize it because that looks too intimidating. But a lot of your textbooks would write it like this. Okay. This is a vector, right? Or the way I like to write it, use letters, right? A, B, C, D. Okay. It looks very clean. So this is a vector, literally. I'm gonna be straight up with you. It's just a matrix column. It's just a matrix column, a column matrix. So this is a vector. Okay. Now, with vectors, we have vector V, and here's how we describe vectors. So the way we describe vectors, instead of, you know how like matrices, we describe it by size. So in matrices, we call the inside of the numbers entries. In vectors, in linear algebra textbooks, or maybe in your class, they're gonna call it components. So if you see a word that says components, a component means an entry in a vector. So for example, this vector V here, right? Or this, whichever. Vector V has four, oh, well, I can't do the finger, but it has four components. Okay? So there are four components, or you can say for entries, but just in case your textbook likes to interchange vocabulary words, they use components, which is the exact same thing as entries for vectors. Okay? Now, another thing about vectors is when we say any vector, but we want to be specific of what kind of vector. So, let me write it. So it's a set of vectors, technically. We say set Rn. So you know how like I'm not gonna bore you with like math languages, but you know how when I say something like in like algebra we write like this, right? For any variable, a variable that can be any number, that can be any real number. That's in algebra we learned that we have to write like this, which means a variable that represents any number in real numbers. Or when we write like this, I guess I can also say like this, right? This means a number that is in a set of positive whole numbers. Or if I want to be more specific, a set of a set of 1 or 0, 0 or 1. So this means so this is a set, and we say like x can be either 0 or x can be 1. Whatever it is, this x is in a set of this, meaning x can be 0 or x can be 1. And if I want to add a 2, then I say then x can be 0, 1, or 2. And then in math languages, x can be any positive whole number. X can be any whole number. X can be any fraction. And then the one that we always use, x can be literally any number that's not a complex number, that does not have an imaginary number, but literally any number. Okay? So what we have right there is exactly how that works, but for vectors, right? This n here represents n entries of a vector. Okay, so we say set Rn, well, or I will have to add this in as well, because not all of us are American. So we say set Rn to describe any vector with n entries. Okay, so the reason why I mentioned this is because depending on what country you're from or what textbook you use, you can sometimes use a math textbook from different countries. It'll sometimes use the curly R. Well, it'll be more like it'll be very curly, a very curly R. I don't know how to draw it exactly, but it's a very curly R. I'll be interchanging with notations like that just for all types of people to get used to it. But yeah, this is, it could be, so if you see this, they both mean the exact same thing. Okay, now let me give you an example of what this means. So for example, right, so it's just like how I showed you, x can be, or square root of 2 is a real number, right? X can be any real number. Is similarly, similarly, the way we're going to write it, similarly, for any vector v, any vector, literally any vector, or AB this is a vector with 2 entries or 2 components, right? This or this. Okay? That's what that means. That's what this means. Okay? All right. So that's how this is used. So if you ever see this, don't be intimidated by it. That's just what it means. It's just to like specify what kind of vector it is, right? Kind of like how we specify what kind of number does that variable represent. Okay? All right. So for example, like here, like what kind of vector is this, right? This vector belongs to R4. Okay? I think some books they call it like subspace, or like it's in the space of 4th dimensions, and I'm not gonna intimidate you with those mathematical words. Okay, trust me, it annoys the hell out of me as a mathematician myself. Okay, so let's go ahead and erase this and start with another vocabulary word. We have another word, and it says standard basis vectors. Pivot columns. Do you remember what pivot columns are? Right? It's one of these. It's one of these thingies. The leading ones. The only one in the column. The only non-zero in the column. This is a pivot column. Right? Or anyway. So, and the way we write this is like E1. Okay? The way we write this is like E1. But how can we be more specific? Right? How can we be more specific? So here's how we write it. Right. So let's do an example. Right. Example. In the set of R3, E1 is equal to 1, 0, 0, right? This 3 represents how many components or how many entries our vector has. Okay? So this is E1. And what is E2? Right? E2 is the second leading one. And then E3 is the third leading one, right? So that's what these E equals. Okay? I do want to mention, I'm going to write this in red. Okay? I'm going to write this in red. So here, I'll write it here. Okay? E4 does not exist in R2 and R4. Okay? So I'm going to be very clear. E4 does not exist in R2 and I'm sorry, what R4? What the hell? R3. There you go. Okay. So it does not exist in R2 and R3, right? Because E4 you need a fourth component. But there is no fourth component in R2 and R3. So E4 does not exist in R2 and R3. Okay? Now, let me go ahead and erase that for now. And I also want to erase, I guess I'll erase everything here as well. Okay. So, just to help you specify better, okay, E4. So when I say E4 in 4, what does that mean? What does that mean? E4 in R4. This means that E4 is equal to 0, 0, 0, 1. Okay? Now, what if I tell you, what is E4 in R5? What is E4 in R5? This means that E4 is equal to 0, 0, 0, 1, 0. Okay? That's the difference. This is E4. This is E4 in R5. Okay? Because it has 5 components. Okay. This 4 just represents the leading one. What row is the leading one located in? That's what that 4 represents. That space, the R space, R5, represents how many components the vector has. Okay? So that's the big difference. That's how we specify, okay, but what is E4? What space? You know, when your professor tells you in what space, in what vector space does what E4 are you talking about? This is what E4 looks like in vector space R4. This is what E4 looks like in a vector space R5, or in the set of vectors R5. Okay? Okay. Vector space, a set, it's the same thing. I think algebraists might be a little triggered by that, but I don't think too much of a perfectionist. Okay, remember how we have 0 matrices? We have a 0 vector as well. So, and the way we write it is theta. So let me define a 0 vector. So a 0 vector, literally, it's exactly what you think, right? It's just like a 0 matrix, right? Oh, there you go. Okay, that's it. It's just a 0 vector with 4 components. Okay, but how do we specify it? Right? How do we specify it? What is this 0 vector specifically? Right? How would you specify this? You would say that this is a 0 vector in R4. Okay? That's how you would specify this. It is a 0 vector in R4. Okay. That's pretty much it. It's not that. It's pretty simple. You just have to get used to the notation. That's all. Okay. So now we're gonna get into matrix equations. So matrix equations. Again, we're going back to a very ugly system of equation, right? How do we deal? Well, I mean, we already learned how to deal with this, right? Just use an RREF calculator. But we can also, I just want to show you that what it would look like in matrix equation form, right? So we learned how to do it in augmented matrix, but what does it look like in an equation, a matrix equation? So what it would look like in a matrix equation is we write down the coefficient matrix, right? This is 1. This is all 1. 1, 2, 3, 4, 5. And then we have 2, -1. And then we have 1, 2, and -1. And then 1, -2, then 2, -1 and -2. Right? Instead of making an augmented matrix, here's what the matrix equation looks like. So we write it like this, and we follow by matrix multiplication, right? A, B, C, D, E. That's what this is. A, B, C, D, E. Okay? And so now this is equal to 10, 17, 9. Okay? Notice that we have a coefficient matrix here, a vector that we have to solve for, right? That's why we say a matrix equation. This is a matrix equation where we solve for the vector, and then this is the vector, that's the answer to, right? So again, when we perform matrix multiplication with this, it turns out exactly like this, right? Multiplying this plus the multiplication of this, plus the multiplication of this, plus the multiplication of this, you're gonna get literally this. Okay? So that's what this represents. So we could write this as a matrix equation. And this is what a matrix equation looks like. In the majority of the times, we can generalize it. So, in other words, since we are able to write the system into a matrix equation, most of the times it's going to be the coefficient matrix, and then the vector that we solve for equals another vector. Okay, and the majority of the times they'll use b, x or v. It's the same concept, right? This is a matrix equation where we have the coefficient matrix, and then we have two vectors, the one that we solve for and the vector that we are given. Okay? So that's what a matrix equation looks like. Now, let's go ahead and we're not actually going to solve this, dear God, no. That's all. I just made that up. But we'll do an actual example. Okay? So let's say that you solved the augmented matrix and you have of course, every system looks like this, where we solve for x. So if we find the solution, we can write our solution as a vector. So our vector x is equal to 251. Right? Because remember, this represents ABC, right? It represents the unique solution ABC. This is what x is. It's the set of solutions. And of course, we can write it as a vector. Okay? So, let me kind of make it easier for you to visualize, right? We've done this before, where we have ABC, right? Instead of writing like A equals B equals C equals, we can write the vector, we can write the solution in terms of a vector. Okay? And you're done. And that's it. So this is a second way of writing your solutions. Okay? Write it, so when they say like write your solution in vector form, this is what it looks like. Now, sometimes we have a system where our, I wouldn't say our answers, but the numbers here, they're all zeros. They're all just a bunch of zeros. So, what does that mean? We say that the system is homogeneous, or I guess chemistry people call it homogeneous, but it's, I actually don't know how it's pronounced. Homogeneous, homogeneous. I don't know. I kind of interchange. I don't know if I spelled that correctly, but this is a homogeneous system. Oh my god, I sound like differential equations people when I say that. Homogeneous. This is a homogeneous system. Okay? This is a homogeneous system of equations. So, and the reason why I brought this up is pretty much when I say homogeneous equation or homogeneous matrix equation, when they say this, they are mentioning this. where instead of a vector b, it is the 0 vector. Okay? Now, the reason why this is such an important concept is because in algebra, right, we're always told, like in algebra, if you have a product that equals to 0, either a or b has to be 0. Or, I'm sorry, if any, some number times another number equals to 0, one of the numbers has to equal to 0. Or both numbers can be 0. In matrix algebra, that's not always the case, right? You would say, oh, well, if a times x is equal to theta, then x has to equal to theta, right? Because, matrix algebra, right? Multiply a 0 vector or multiply a 0 matrix to another matrix, it'll just become 0. Well, that's not always the case. In matrix, with matrices, yes, but with vectors, that's not always true, right? We can have a non-zero vector and a non-zero matrix, and it'll turn out to equal a 0 vector. That can happen, and we call that a non-trivial solution, actually. So, more vocabulary words. I know. If x is equal to the 0 vector, which is because it looks obvious, right? If x is theta or a 0 vector, then this whole thing, everything's become a 0 vector, a 0 matrix, right? So and it's very clear, right? So if x is equal to a 0 vector, then, and what we say, then we have a, and they call it a trivial solution. And we have a trivial solution. In math language, trivial means obvious. That's just how math people, or that's how math nerds say obvious. They call it trivial. So if some some math jerk was like, oh, that's so trivial, they're just telling you, oh, it's very easy, it's so obvious to solve this. Those math elite people, yeah, they use this word trivial. It's what happens when you lose your social intelligence. But if x is not equal to a 0 vector, okay? If x is not equal to a 0 vector, which can happen, which does happen, in fact, it's not rare, it's really not rare, then we have, this it's pretty easy to remember, a non-trivial. We just say non-trivial. Okay? This is a non-trivial solution. It's not so obvious, right? Not so obvious, right? X is equal to a 0 vector. Oh, okay, that's our solution. We're done, right? Oh, it's not equal to a 0 vector? Oh, crap, then we have to do more. We have to do more to find what is this vector specifically? What is x specifically? That's why we call it a not so clear, a non-trivial solution. Okay? To recall, what kind of system is this? What kind of system is it? This is a homogeneous system, right? Because everything here is a bunch of zeros, right? So, we're going to turn this into a matrix equation. I lied. We're not going to actually solve it. Turn it into an augmented matrix, right? We will turn it into an augmented matrix. Whenever you have a homogeneous matrix like this, this side will always be 0. Okay? If for some reason you have an RREF and a number comes out of nowhere, there is something wrong with the program. Because you should not have anything here. If you're given with just zeros, it should always stay with zeros. Because, if you're multiplying it, adding it, what kind of, multiplying zeros, adding zeros, only zeros should always come out as zeros. Okay? So this should always stay as zeros. If it comes out with any number, there's something wrong with the program. or whatever calculator you're using. Okay, so let's go ahead and RREF this thing, right? So if you use an RREF calculator, all right, and we have our RREF matrix. So here we go. Okay, as you can see, this is what a non-trivial solution looks like, right? It looks like, everything should be 0. Yeah, but that's not the only solution we have, right? Yes, we can have, x, y, z, w. They, let all that equal 0. Then yes, that's, it's very clear. It's trivial. But because there does exist, look at this. Look at this. We have free variables. Because we have free variables, there are infinitely many solutions, meaning that it's not just zeros. We also have other solutions. We have other vectors. That's what that means. We have a non-trivial solution. So by writing it, so again, we're going to write it back in systems of equations. So we're going to write this back. If I can stop moving. So I'm going to write this back in terms of systems of equations. We have x. I'm just gonna quickly write it. So right, we have 6. That's 6w. So w is our free variable. W is our free variable, and we have this is negative 6w. Y is equal to 2w. And then z is equal to negative w. Right, I'm just writing the answers. I'm just kind of, pushing it to the other side. Okay. So we have our solution here. Okay. Can we write this in terms of matrix equation? Yes, we can. Yes, we can. And here's how we write it, right? So this, because we already having x, a vector that we are looking for, a coefficient matrix times a vector equal theta, where a vector finds our solutions. Okay, that's what this represents. Okay, our matrix equation, V is our solution. However, we have infinitely many solutions because we have a free variable. And so the way we write it is, okay, write your solution in vector form, and here's how we write it. So our V, oh, I'm so sorry. I forgot W. Almost forgot W. Okay, we almost forgot W. Okay, so V, so if we want to write our solution, we can write it in vector form. So notice that V is equal to X, Y, Z. Let me just rewrite this so that you don't get lost. Okay, but notice that everything is in terms of W. So this is technically X is equal to negative 6W, Y is equal to 2W, Z is equal to negative W, and W is W itself. And guess what? In matrix algebra, we can actually factor W, right? Because W is just, it's just any number that it represents. So we can actually write it like this. And this is how you'll mostly write infinitely many solutions in vector form. We have negative 6, this is 2, negative 1, and 1. Okay? So we have this. So now let me go ahead and I'm going to crouch. Let me use blue to write our solution. So here's how we write our solution. Now that we know now that we know. So the way we write our solution is very similar, right? We write S. Okay. What is S? S is our set of solutions. So S is equal, and then you write a very long bracket. So S is equal to any real number W that's in the format of that's multiplied specifically by a vector, -6, 2, -1, and 1. For any real number W. This is how we write our solution. Okay? So this is how we write our solution. Our set of solution is any number that's multiplied specifically by this vector. So any vector that's in this format is the solution to our homogeneous system of equation. Okay? And that is how we write our solution. Okay? And that is it. That's matrix equation. That's pretty much all we need to know. There you go. And that's how you find your solution in vector form. Okay? Alrighty, let's delete this. That is it for this lecture. That's it for lecture 2. It's a lot of content for matrix algebra, but it's okay. We literally hit like a very good, solid backbone of linear algebra. Okay? So again, just a reminder, there are problem sets in the description of the video, and just practice that. Use an RREF calculator, please. And yeah, just practice and you'll get more comfortable with matrix algebra. Okay? I'll see you guys in the next lecture course video. Thank you so much for watching. And I'll see you guys. See ya.